And now we have medal lectures by the 4 medalists, and we start out with Gerhard Haerendel, Fascinating Plasma Structures, and this is the Dominique Cassini medal lecture. So Gerhard. I'll give you a sign maybe 5 minutes before.
That's fine. Is there a pointer and this is transport here?
That's a pointer that advances, yeah. and the green one is a pointer.
This is a pointer, okay. Yeah. But when I was invited to give this lecture, I was thinking what physical property or I could put as on a symbolic place of my scientific work, and it came to magnetic stresses. This is not very nice. I think if it were the Planck constant, it would be better. But so this is what I worked with, and I want to give you 3 examples. One, where magnetic stresses help to accelerate a big mass, a comet. The second, where they serve as energy reservoirs for something, namely for auroral arcs. And the third, where they act as a net against gravity. Okay, so I will start with the cometary plasma tails, or I could say it's the solar wind's magnetic gear. It uses magnetic stresses to accelerate something. Here you see some comet tails, and you distinguish, for instance, on the left one, no, that was wrong. This is a pointer. You distinguish the plasma tail, which is almost strictly pointing away from the sun, and the dust tail. Or here, Comet Mirkos, wonderful plasma tail, and you see there are a lot of structures here, and I will come back to that. That these comet tails are pointing away from the sun was known already to the Chinese, and possibly before. In Europe, it was Peter Bienewitz who discovered that, and then there was Ludwig Biermann, who not only noticed the same thing, actually I think he learned it from Hofmeister, but he interpreted it as a fact that the whole solar system is filled with some corpuscular radiation radiated from the sun and interacting with the comet and creating the tail. He didn't know what the process was, but Hannes Alfvén, again, difficulty here, Hannes Alfvén recognized that magnetic fields play a large role, and you see how the magnetic field carried by the solar wind is draping around the comet head and is pulling on the cometary matter, and accordingly these distortions of the magnetic field, which really exert the pull on the plasma, are called Alfvénic wings. Now it was Biermann's interest in the subject of comets which then led to the creation of the institute, of which I entered on the very first day in 1961, and which was headed by Reimer Lüst. And the first goal was to create something that is reminiscent of the interaction between the solar wind and a comet. It took 25 years from this slide to the next one, a quarter century of activities passed with barium cloud experiments in the ionosphere first, and later on in the solar wind. So we evaporated a gas of barium atoms, exposed it to the solar UV light. Within half a minute, the stuff becomes photoionized, and then there's a plasma, and that interacts with the environment. In this case, from a satellite at 100,000 kilometers distance from the Earth, and this was in 1984, 1985. And here you see a picture of the first comet, and there were many surprises, one of which there were 2 big surprises, and they are mentioned in the graphs on the right-hand side. The first one was that the comet head stayed more or less where the satellite was. It was not moved by the solar wind. Instead, it moved slowly to the side. This is the yellow arrow. The reason for this is, and this is shown in this graph here, so the lateral motion, and it stayed ahead with the comet, with the spacecraft from which it was produced. The reason was, and you will see for the lateral motion, that ions are extracted from the boundary of this and accelerated by the solar wind, and since it's barium, they have huge gyroradia far away from here, and there's a recoil. It's like as if there was a jet engine here, and the recoil was moving the comet head to the side. Now, why it didn't move with solar wind in that direction has to do with the formation of the tail, and I will come to that. Now, here you see a movie, first in two parts. The first was observed from Arequipa, Peru. It's 1,000 kilometers distant, so we had to find good positions to triangulate, excuse me. And, no, I have to go back. I'm always hitting the wrong button here. No, again. I have to go one slide back. So now, here. Good. So what I wanted to show is, while you read this here, yeah, I have to show that this was the position of the spacecraft. These are only minutes, so the life of the comets was short. This is the direction of the solar wind, and there is the direction of the electric field. And you will see how this comet head is forming, and you will see the effect of the recoil. It's very strange. The solar wind comes from here, but the highest mass is concentrating here. It is collected, as we call, like a snowplow, because as the field moves in, it drags the mass with it. And so it comes first from behind. It's very strange. Then it comes from the side, where the electric field is, in this case on that side, is creating the recoil, and you will see the center of this cloud is slowly moving to the side. This movie is only 2 minutes, so it doesn't last too long, but you will see how long it takes before it achieves the form of a cometary head. Now you see here are the ions extracted. This is the concentration of magnetic field and mass from the side, and slowly, slowly it will form something that you would have expected and that we did expect before we did the experiment. Okay, well, I'll give it a few more seconds so that you finally see here's the beginning of the tail, and this is now forming sort of a blunt head slowly, as you would have expected. Now in the next movie, I can stop here. In the next movie, we use a different camera. It was operated from an aircraft flown out of Argentina. Now the scale is different. It's 5,000 kilometers here. And I should mention these two objects were the biggest objects that man ever created, the biggest coherent objects with the help of the solar wind. A length of 10,000 kilometers visible, and a cross-section of 800 to 1,000 kilometers. So this was something very rare and will not so soon be repeated. Now the reason for the fact that the head stayed with the spacecraft and slowly tail formed was that the momentum imparted by the solar wind was transferred through the cloud, because on the front side there is a magnetic pressure which acts upstream and magnetic tensions of this field which work downstream. And so they are in balance on the front side. On the rear side, magnetic pressure and magnetic tensions work in the same direction, and they accelerate ions out here, and they create plasma structures. So this goes on for a while, but I think you see the essence of it. So now we come to natural comets, and one of the striking things, as I pointed out already from this comet Mircos, are these nodes in the structure. And they, of course, good landmarks to measure the acceleration. And here are curves of Comet Austin, which we did in 1990, and this is from an old publication by Rea Lust in 1962 on this Comet Mircos. And the idea is very simple. There is momentum transferred via the Alfvén wings, the strings of magnetic field draped around the comet, and so one just compares the amount of mass along such a streak through the comet head with the speed at which mass is covered by these Alfvén wings, and that gives you the basic time scale. Then there's a compression of the magnetic field and so forth. But I don't want to go into these details. I want to show you one thing, namely how one can understand the origin of these structures. This is a simulation from one of my students, and here you see again this drawing from before, but if you create a small perturbation, then suddenly these things are out of balance, and the ions which are launched on the rear side of this first perturbation are then pushing the front side of the second perturbation, the second enhancement here, and so this splitting of the distribution is increasing, and slowly these blobs of plasma move away, and in all cases ions are accelerated on the rear side and are impinging on the front side and compress the field. So the ions always move a little faster than these structures. So this was an insight which we got from these experiments. There were, of course, a lot of other things which I will suppress here because I want to give you just some examples how fascinating the research in magnetic shear stresses can be. Now I come to auroral arcs. This is one of my really beloved subjects, and you will see a few movies and you will see that it is almost impossible to really describe what happens in auroral arcs theoretically. But we give it at least a try. So I talk here about stress relief because that is what is powering the acceleration region of auroral particles. Now first we start with the environment. Here, back. It's difficult with this thing. Yeah. So there is the sun here. There's a front coming on, impinging on the Earth's magnetosphere, and if there's an enhanced pressure or a reversal of the magnetic field so that reconnection can occur on the front side, then the solar wind can grab the Earth's magnetic field and pull it on the rear side. And this is the essence of creation of magnetic substorms and storms. And here you see a simulation. You see such a front coming and how it really, of course, these are many hours in a few seconds. And as a consequence, there is a substorm starts around the auroral oval, around the pole, here as seen from a satellite. And this is communicated by currents from which are initiated by the activities of the plasma in the outskirts of the magnetosphere, and in the tail in particular, is communicated by electric currents which then flow into the ionosphere and close in the ionosphere. Now you see it now from an all-sky camera, so a cross-section of about, this is difficult, that's when one makes these mistakes here. I have to go twice back. Maybe it works now. Yeah, you see the development of a part of a substorm visualized by an all-sky camera from the ground with a cross-section of maybe a few hundred kilometers here. And here you see a wonderful drawing from Moltke of an auroral arc, and you see these striations here. And they are very significant. They signal something. And that we will go to. Now what happens is that in the dynamics of the plasma under the reconnection and the magnetic forces communicated by the solar wind, these magnetic shear stresses pull the plasma from the front side where reconnection occurs across the polar cap and stretch the field into the long tail. And looking on the pole, this means the plasma, the feet of these field lines are moved from the front side across the polar cap. And then, since near Earth, the magnetic field is incompressible, it must set up a vortex motion, two vortices, one on the morning side and one on the evening side. However, the in the first place, the polar cap is growing because the magnetic field is now, the field lines are now open, which were closed before because they are transported from the front side into the tail. Now, eventually, this so-called substorm starts, and reconnection occurs also on the rear side. Plasma snaps in again and builds up a pressure maximum in the night side. And this is this pressure maximum, and it pushes the plasma away from midnight towards morning and towards evening hours, or towards the sun in general. And these forces bend the magnetic fields here. So this is the force sets plasma into motion. It carries its magnetic field in this direction or in that direction. So it's bending the field, and there are then shear stresses initiated, which are transferred by by field-aligned electric currents down into the ionosphere, and they close there, and that means that the forces which are initiated here are transferred down and are communicated to the ionosphere, which is dragged in the direction of these forces, and this goes under friction, and that means there is dissipation. So this is the basic physics, how the solar wind energy and momentum is communicated to the ionosphere through these current systems. And this happens in a way that first, when the plasma is set into motion, like here, an Alfvén wave is launched, which is an elastic wave propagating along the magnetic field. It hits the ionosphere, is reflected. It's a complex transient phenomenon, but in some cases, one can describe it as a quasi-stationary system with current flowing down in a sheet on one side, closing in the ionosphere, dragging the plasma with it, and returning to the source region where the force is initiated or applied. And then, of course, the field lines are bent, and, for instance, there's a transverse component out of the plane. It is very small, this component, but the forces behind this are big. Okay, now, back again. So, now you see slowly developing auroral arc, and you see the complexity of it. So what happens is, written in a few lines here, what an auroral arc really is a fast way of releasing these magnetic shear stresses. So the shear stresses by this current system coming down on one side, closing on the ionosphere, and going up. And when the upward current is very concentrated, field-aligned potentials develop. That means there is a voltage along these field lines, and when the current is up, it accelerates electrons down and ions up, and that, when the electrons hit the ionosphere, then they create the auroral arcs. And you can imagine that this is a rather complex process, because you see what is happening here. It's, the arc is splitting, developing folds, and all of this. So at present, we are not able to describe all of this, but we can make simple models. And the simple model is that the arc propagates into this circuit here, current down, horizontal, current up. So there is here the shear stresses are higher on that side, inside the circuit, than they are outside. And as the arc propagates here, it releases the shear stresses, and this magnetic energy is what is powering this accelerator, which accelerates the particles. So this auroral process is a basic cosmic accelerator. It can work on any magnetized star, and probably is. So, next slide. Here you see a detailed model. Here we see these potential lines. There's an upward current region. Here the arc moves to the right, and as the electrons come down, they create these the aurora and these striations, or rays, which you have seen in the picture by Haerendel. And what happens here is that because of the potential drop, the upper part of the field lines don't do something that the lower parts do not notice, because they are electrically coupled. And what happens is that the shear stresses of this bent field lines, they are relaxed. They are suddenly as if you take a stick and drag it to a porridge or something very sticky, and it is too thin, it breaks. So what will happen is that the stick is releasing the shear stress. It moves from here in this direction, like here, But since, other than in the example of a stick, this all full of magnetic field is incompressible. So the field has to return, but not fully. And the difference in shear stresses between this field line and that field line is what supplies the energy to auroral acceleration. So we call this magnetic fracture, and this happens through these potential differences. And here in the next slide, we will now look up the field lines in the next film, look up the field lines and see how these shear stresses are released. So you see motions which the electrons receive before they are accelerated here in these transverse fields. On one side, the active side out of the plane, and here into the plane. Now we are looking up the field line. So the active side is here. The arc moves in this direction, and this is only 10 kilometers or so. And here the electrons have received a lot of energy. This is the first stress relief motion, the fast one, but the return, because of the incompressibility of the field, is seen here. It's much less active. It is, but one can measure it. And so what is to be taken from that is auroral arcs are not a product of energetic particles coming from the sun, entering the Earth magnetic field, impinging on the ionosphere. No, it's of magnetic shear stresses, which are set up by the dynamics of the plasma stirred up by the solar wind in the outer realms of the magnetosphere. Now I come to my last topic, and this is ongoing research. It's not even accepted yet for publication. I have still to deal with the referee. But I want to tell you what I'm working on right now. And there is a phenomena which is very fascinating and has fascinated me since long, but I just started a month ago to work on it. And these are the prominences. Obviously, magnetic fields play a big role in sustaining cold matter of the temperature of 8,000 degrees in a 1 million degree coronal environment, and densities orders of magnitude higher than that of the corona. So how can this happen? How can they live for weeks? Like these quiescent prominences, now looking from above, you see these structures, they can extend over 100,000 kilometers and live for weeks. So how is this matter sustained? There were simple theories developed, and the first one by my thesis advisor, Arno Schlüter, together with Rudi Kippenhahn, and that was shortly before I entered the Max Planck Institute. And later on, so the idea was that there are magnetic fields extending from a region of one polarity to a region of another polarity. And I should say these prominences, or when you look from above, they are called filaments. They always are aligned along regions where the vertical magnetic field that one can measure easily on the sun by the Zeeman effect, where they change direction. And so this is the polarity inversion line here, along which this thing extends. And the idea was that these fields are somewhat indented, and by the magnetic tensions here, they support the matter against gravity. This works very well as an equilibrium, but it's completely unstable. So the theory, although nice and probably distinctly correct, this does not hold out the long lifetimes of this. So, and this is, of course, theory has been made some 50 years ago, and a lot has happened meanwhile, also in terms of observation. First, I show you again here. This is now seen from above. This is called a filament, but it has, looking from the side, the appearance of what you have seen before, and you see the polarity changes. You cannot see that, but what you can see is that these fibrils seen in H-alpha in the chromosphere are sort of tangent to this line. So the magnetic field also that forms and holds the matter chromosphere in the corona is really very much aligned. It crosses slightly this polarity inversion line, and these field lines reconnect and form a structure which is basically horizontal. And it builds up over weeks or days and weeks to form the magnetic support of the filaments or prominences. And now it's very surprising when you look now at pictures which are recently have become possible by the Hinode, Japanese Hinode Solar Observatory, that these structures move vertically. The field is horizontal, and the structures move largely vertically, up and down. Sometimes you see horizontal structures. What is happening there? And this is what I'm dealing with and what I'm hoping to help solving. Maybe I'm completely wrong, as my referee thinks, but here you see a better movie. And these are called heteroprominences because the matter is falling largely down. Then there are some blobs here. Sometimes you see matter moving upward or holes moving upward. In the foreground, you see the spicules and the granulation of the sun. So this is fantastic. It's only a few hours that you see here compressed in time. The velocity, and this is the funny thing, there are constant downward velocities of the order of 10, 15 kilometers per second. The structures have a substructure of about 300 to 500 kilometers. And so how is that possible? Now, if you take the gravitational acceleration of the sun and calculate which start from rest and let something fall, after which distance does it reach about 10, 15 kilometers per second, then the distance is 500 kilometers. So if they go on and fall over 15, 18,000 kilometers with a constant speed, there must be some drag acting upon them. And it must have a scale of the order of 500 kilometers. And that led to the idea that is outlined here, that first of all, plasma is carried upward invisibly because it's hotter than what you see there. So it doesn't appear in H alpha. It may have, instead of 8,000, 40, 50,000 degrees. We don't know how it comes up, but it always starts at the top, or most often starts at the top. And then it's assembling there, it's cooling, it becomes visible. And since it is cooling, the magnetic field the pressure is lower, the magnetic field compresses it, and it forms such a thing here, which is reminiscent of the original idea of Kippenhahn and Schlüter. And eventually, and this is the supposition, the conjecture here, these structures separate and form blobs, droplets, which are falling down. And so the idea is to describe these heteroprominences, these downflows of matter, as a sequence of droplets, like the vernal fall in Yosemite. Look at the water coming down a waterfall. It consists of a lot of structure, small structure falling down because of the air, and there the air exerts the drag on the horizontal field. And so finally, as the droplet falls through this horizontal field, it distorts the field, and this is what exerts the drag. There are Alfvén waves, so elastic waves along the magnetic field generated. They propagate away, carry the momentum away, and we go so far as to suggest that this energy, which is taken out of the gravitational energy of this falling droplet and excites the waves, that it is processed in this horizontal structure of the magnetic field and it forms a cascade in frequency and wavelength space, and can be in part reabsorbed by this blob and heat the plasma, because otherwise it would become too cool. But it stays at constant temperature. Time is half a minute or something, so it goes very fast. So it has to be heated by falling down. So probably once the plasma starts moving from above, it falls slowly down, liberates its gravitational energy by creating the wave process, reabsorb heat it and heat the plasma again. And so in the end, the plasma is heated by the gravitational energy that it has liberated itself. So far, so good. Maybe I'm on the wrong boat here in this theory, but it has some attraction, at least for me, to understand something that we have been worrying about, or scientists in this field have been struggling with for more than 50 years, and maybe this is in the direction of a solution. I just want to demonstrate to you some examples how fascinating structures imposed by the magnetic field can be. So the summary here is cometary tails are generated by the pull of the solar wind magnetic field, and plasma clumps along the tail are a sequence of slingshots, each firing ions on the next one. These were the cometary structures. Magnetic shear stresses transmit forces from the outer magnetosphere down towards the ionosphere, and eventually these structures break, they decouple from the ionosphere, and it's like breaking a stick which is drawn through the sticky porridge of the ionosphere. And the last one is, well, I just explained it, the conjecture that these plasma droplets are reminiscent of droplets in a waterfall, and where the air drag is here provided by the horizontal magnetic field. In the end, I come back to what I said when I got the medal some half hour or 1 hour ago. I'm deeply indebted to the team which has been working for me, like in some of them for almost 40 years. And there are a few names, there are certainly many more, and there are a lot of colleagues internationally who supported me and with whom I had the pleasure to work. Thank you.
We have time for some questions. I have a problem of seeing here, but... Well, I have actually one. You are one of the few examples who has worked both on the plasma environment of the Earth, where we typically have the ability to make in situ measurements, but don't get a picture because the material is so thin and tenuous, and on the solar side where we can't go to the sun and make measurements, but we can take pictures of it. So what do you think we should do to enhance the crosstalk and collaboration between these two communities?
Well, this is certainly a very important question, in particular at times of transdisciplinarity, and actually that this is not transiting too much to go from the is weakly ionized to the chromosphere on the sun, which is also weakly ionized. But when you then see that there are big differences in parameters like 10 orders or 12 orders of magnitude in density, then you see that there are new things appearing in the new environment. And when you go to neutron stars, then it's even worse so. So what it means is that somebody experienced in one field, let's say the magnetosphere, and he wants to carry his ideas to another magnetized environment in the universe. He first has to be a student and learn a lot. And so the first thing is to go to conferences and listen and talk to people and learn before you really can communicate, because there's a lot to be learned before your ideas can be transferred to something else. So joint symposia, like this year will happen in Sicily in September on plasma astrophysics. These are opportunities to communicate and to learn what the problems are in another field. So,
thank you. Are there other questions? If not, let's thank our speaker once again.